Good evening. So here are the rules. You guys brought questions, I'm sure. So here's what I will answer and here's what I will not answer. I'll put my one rule up. Specific. So an example of a specific question. Dr. Morrison, I was working on non-restoring division and I don't understand the purpose of the bit flip. Can you discuss this and tell me why we're doing that? Unspecific question. Dr. Morrison, I don't understand multiplication. Can you do that? You guys understand the difference? Show me that you've done a little bit of work and I'll help you out. Okay, so does anyone have a question? No? Everyone's going to get a perfect score on my exam tomorrow? By the way, we will keep going until the questions are done. I've done this in the past, and one time it lasted 3.5 hours. So, yes.
When you're doing the C of this assembly language, can you go over the when we're doing the branch equivalent and branch not equivalent?
Sure. All right, so let me page down all the way to this solution. All right, so the way this question works, you will have some sort of C code. You will have an initialization of registers. First off, before we get there, why do you not have to write any code for these two lines? It's assumed. Why is it assumed? What did you learn early in the semester that makes this a valid assumption? Compiler, what's the phrase I say all the time? Yeah, compiler-driven encoding in the micro engine, right? So the compiler, now that you guys are working on this in code, in your project that's due next Sunday, you load this in the data memory to start by importing it from text file, right? And you're importing registers. You'll be loading S1, S1 is 0, and S2 is 3, right? So anything that you put from the .text files is the compiler-driven encoding of the micro engine, which means you don't have to do it. Everything else you have to do in this problem. All right, so the specific question is about this branch if equal, branch not equal. So we have done all of this, and we get down to this part and this part. All right, so the first one that we're working on here is while array first does not equal 0. So we have done some sort of load elements, and we have a temporary register. We'll call it T1 just for this instance, and we're comparing these values. Right? So what we need to do is branching indicates I want to get all the way past here. So we have this one bracket, we have this one bracket here, and I do not want to do this code. So I look at this comparison here and I say, what do I need to do to not execute it? So if I do want to execute it, this register should not be equal to 0. So when do I want to branch? Branch if equal to 0, right? So first thing I do is I want to do BEQ. So does anybody remember? Okay, first of all, what type of instruction is a branch instruction? I-type. So if you look at the MIPS screen sheet, you will see that if RS equals RT, right? And it's going to say register RS equals register RT. In fact, I should probably just bring up the green sheet. It's going to online here. And I can show you specifically. You will have log in. Some sort of password. Oh. Give it a split second to think. And so you will have everything on this front sheet, reference files. We have a screen sheet. You can open it here. All right, the only thing that will be blocked out tomorrow, this will be crossed out. because that is one of the questions. So everything else on there, on this, it will be two-sided. Everything on the front and back will be there, right? So we're going to compare branch instruction. So we have decided we're going to do BEQ, so you can see, let me cross this out, and let me do one better, let me save as. Nope, didn't want it to open there. All right, so now I can zoom in all I want. So branch equal. So this right here is what I was drawing up on the board. And what that means is the value, I'm going to zoom in even closer for those of you in the back. So here's what this means. If the value of register RS, which is uppercase RS, is equal to RT, then the next value of the program counter is going to be equal to PC plus 4 plus branch address. So I need RS, a value from RS, and I need a value from RT. So we go here and we see it's 4 hex, which you'll deal with a lot more in your coding projects. But when we go here, we go down more. We see our I-type instruction. What they're talking about is the first register is in RS, the second register is RT, and the immediate value is here. So we have to have some sort of numerical value in the code before the code runs where we actually need to know this value. Now, when we get into section 8, when we get into multiprocessing, we're going to learn that that's a lot harder than you think, and we're going to talk about branch prediction and some really cool stuff on that. But anyway, so this is what you need to know. These two values, we're going to go into the registers. We're going to get those values out, and they're going to go into the arithmetic logic unit. The arithmetic logic unit compares if they are equal or not. If they are equal, it's going to do a value of 1 and go to that AND gate with the branch control signal. Now, probably the part that's the hardest to figure out, and took me a little while, admittedly, when I first started learning this material, was how do we calculate this next value? So here I've calculated the value of 6. So you know that it's PC plus 4 plus the immediate value, and I want to get from 16 to 23 in this case. So PC plus 4 means that I've already accounted for the next instruction, right? And why can I say this? Does anybody remember why? Why do we automatically have PC plus 4? Byte addressing and what specifically about the data path?
Because it adds with
Correct. So when we go back here, we can see exactly right, because it adds. So when we go to the data path, oh, actually I can just stay right here. So every instruction, we get the current instructions, which as you said is an address, byte addressing, comes here, it goes to an adder, and we automatically add 4, right? So it goes on from there. So we get down to the full data path. What we find out is that that result comes here, it's added, and is coming out here, it's coming out here. Now, there's another important thing. Because of byte addressing, this value that's coming out of the immediate from your green sheet is coming out here. It's sign extended, goes through here, and we go to this SL2. What does that mean? Shift left. Why are we shifting left by 2? Multiplying by 4 because of byte addressing. So that means that the value that's in the immediate is going to represent the number of instructions you want to branch past minus 1 because we've already accounted for it here, right? And then they're added together, and then they come back and tell me the actual next instruction that I want to go to. So what this means in this branch instruction, branch equivalent, I figured out that I want to get to 23. I wrote everything out as I showed you last class, kind of the directions, and I figured out that 23 minus 16 is 7, and that I want to subtract 1 because I've already accounted for this PC plus 4, so therefore it's 6. Right? So that's how you do that. And so the directions I showed you last time, I said write out all the other lines of code and then go back and figure out the immediate values you want to put in. So that's how you kind of formulate a branch equivalent instruction. So for the branch not equal, the C code that we are doing has this first less than or equal to second, right? Now here's the interesting thing. And this is why we, if you recall the topical guide objective here, 5.14. Get familiar with this one tonight, because this is the one we worked on, and you will see one of these 4 will be on your exam. So the variance will be here. No tricks. These are all 4 possible combinations. So what we've done is I've identified that I want to have I is less than or equal to j. So here's what we got to do. We have 2 types of instructions we can do. We have set less than, branch, 3 types. Set less than, branch equivalent, branch not equal. If you look at your MIP screen sheet, I do want to point out one thing. I'm limiting you to these instructions right here on this left here. This pseudo instruction set, which I will also have, which I have blocked out. So you have branch less than, branch greater than, branch less than or equal to, branch greater than or equal to. These are the 4 combinations that I produced in the TGO. Those pseudo instructions means they're not real instructions. So what happens is if you write it in code, here it's Verilog, it will actually compile it down to the same instructions that I showed you in the topical guide objective. It will not actually do, there is no branch less than, that's why it's called mnemonic and actually not the name. So these are not actual instructions, they are not real. Move does not exist in MIPS, even though it's in a lot of other instruction types. We use add or add immediate to accomplish that. So what's going on here is we need to figure out the exact combination we want. So here we had I is less than or equal to j because we had star first is less than or equal to second, right? So what we need to do is we need to come across the situation. If I have S2 and S1, which in this case is second and first, what I'm doing is I'm saying if second is less than first, set T0 equal to 1. And the reason why I say that is because you want to do that, you want to figure out the exact opposite combination. So if I is less than or equal to j, that means I want to do the code, which means branch if j is less than I. So here what I've done is I've set less than, if j is less than I, set T0 equal to 1. And then the next step, this T0 is equal to 1, and recall going back to the MIP screen sheet, MIP screen sheet, there we go. Well, I have to have 2 register inputs, right? Branch on equal, branch not equal. RS does not equal to RT, RS equals to RT. I can't use an immediate value. So, if you recall from here, we actually have a register 0 where it's automatically stored as 0. So what we did, we said I know that t is equal to 1 if I want to branch if t is equal to 1. Therefore, branch not equal, t is equal to 1, then it's not equal to 0. And then I put in the branch address. So in that case, that's exactly what we did in the solution. We go here. Section 5, right? So we go down here, and we see I've set less than T0 and A2. So T0 is where I had the pointer to first. I said, well, I want that to be less than second, so therefore it goes into T4. And then if T4 is equal to 1, that's when I want to branch, right? So therefore, if branch not equal 0, and therefore I branch the number of instructions. So in that code, I had set sum plus equals array of first, which we had actually already calculated up here in the loop. So I don't need to recalculate it. So I just said sum add instruction sum equals sum plus array of first. And then I only need to branch past one instruction. So I was able to go back to the instruction and put in a 1. So same thing with these other types. Here's what happens. We go to the, we go back to these TGOs here, 5.14. They say if I is less than or equal to j, that means I want to branch if I is greater than or equal to j. So I want to figure out, is I less than j? So here we say if I is less than j, then put T0 there, right? Next, branch if equal, S1 and S2. The reason why is because if they're equal, I want to branch, right? If they're equal, automatically I want to branch. You could do these two instructions in an opposite order as well. You would just, the number here would have to be one more. That's the difference. So from there, I know that if I is less than j, then I don't want to branch because it'll be 1. So be any. There's another right answer here. What could I do that's differently to get the same correct answer? I'll give you a hint. Let's say I did this. Let's say I did change this to S2 and S1, right? So that means T of 0 is equal to 1 if j is less than I. So here's the condition. We can do the branch again. So what's going to happen if I have this condition where I is less than j? What's the value of T0 going to be? 0, correct? So that means if T0 is going to be 0 and I want to branch, in the opposite condition, what could I change this to? Branch equal. Okay. So this is another completely correct answer. Same thing with I is less than j. First you set S2 is less than, so if j is less than I, it equals 1. And then that means I want to branch if I is less than or equal to j. So I branch each time if they're equal, because I don't want to do the condition. And then branch not equal if T0 is 0. So I've flipped it around. So same thing, we could do this. We could do S1 is S2 and change that to branch equivalent, and that is also a correct answer. And then finally, if I is greater than or equal to j, so you branch if it's the opposite condition. So in that case, it's I is less than j. So you set less than. T1 is T2. If I is less than j, it should be 1. And therefore, if I is less than 1, I is less than j, this would be 1. And that should be branch not equal. Why is that branch not equal? Why was I wrong? So what if I set less than, if I is less than j, what will the condition if we've met the condition here? What's the value of T0 going to be? 1. So I had branch if equal, but I want to branch if we've met this. So I want to branch if it's 1, so therefore I had branch if equal, so I'd branch in the opposite condition and would have failed. So it should be branch not equal. So here are your steps to solving this problem. I'm going to do a little notepad here. Notepad. So step 1. Identify the opposite case of the code. And for example, if I is less than j, then the opposite case is I greater than or equal to j, right? So that's the first thing you do. Put it in the comment, dash dash. You can go like this. You go dash dash. You can write whatever the heck you want. The compiler won't find it, right? So I'm like, you can go, this exam sucks, right? Compiler won't find it. Step 2. If it's I less than j or j less than I, then you already have a branch. You've set less than, and it's 2 steps instead of 3. The third step accounts if there's an equal in your case, right? So if opposite case. We'll call this the opposite case because that's the branch, right? Then the first thing you want to do is set less than first, second, and then you want to do temp register, right? So when I say first, so here it's like first less than second. Now I know in the problem I use first and second, so maybe I should change this to first val greater than second val. So it changes to first val, second val. So example, set less than T4, S2, S1, if, therefore, opposite case is S2 less than S1. Does that make sense, what I've just written here? Okay, so, therefore, it will be 1. Well, put this all together in just one. Temp reg. Therefore, temp reg equals 1 if opposite case met. And then branch not equal. Temp reg 0 num instructions. Meaning that if it's 1, that means you want to see if the case is actually met. And if you have to have 2 registers in there. So if it's 1, 0, we're going to branch. Otherwise, we don't want to branch and just continue going. So in this case, we have I is less than j, where I is S1 and j is S2. So tell me the solution. Now that we go through these first 2 steps, tell me the solution. I want somebody who isn't as confident about it. I want you to try it. You fail it here, you get to make a mistake, means you get it right tomorrow. So somebody who's like, if you're thinking, man, I don't know the answer to this, raise your hand. Okay, so Tony Leha was the first one up. So you beat everybody by a split second. So give me your case. What's the first thing I need to do? I is less than j. Actually, let me make this I is greater than j because it's like the solution's in the case. So I is greater than j. So what is my first step? Reading from here. And so what is the opposite case? If I want to do the code, if it's I is greater than j, so what's my opposite case? When do I want to branch? Less than J. And what else? Do I want to do the code? If I is equal to J, do I want to do the code here? No. Why not? No. Why not? Want to phone a friend?
Yeah.
All right. Who wants to be his phone a friend? Yeah, McKenna.
Less than or equal to J.
Yeah, less than or equal to J. And the reason why is if I want to do the code when I is greater than J, then everything else that does not count for greater than J should be in my opposite case. So if 6 is greater than 5, I want to do the inside of the code. If 6 is greater than 6, doesn't meet it. So my opposite case is I is less than or equal to J. So the first thing I want to do, we have our less than here, right? So I have an I less than is part of this, correct? One thing I should change, contains. So now, Tony, second step. Since it contains I less than or J less than the I, correct?
Right.
So what I want to do here, what's my next step? Are you able to read this? With good eyes?
Is that 5? SLT?
Yeah, what does SLT stand for?
Shift left? No?
No.
Okay.
Also, make sure you make that F really strong and shift left. Otherwise, it'll be a different word. Then it's also wrong in multiple ways. So what is this?
Set less than.
Set less than. All right. Right? So what does set less than mean? I have a temporary register that I'm going to set to 1 if first val is less than second val. Right? So what is my case in my opposite case? So I have a less than here, right? So what's the order going to be in this algorithm that we're coming up with here?
First value.
What is first value?
I.
I. Very good. So we have a SLT. We'll call it T2 for Judgment Day, which is tomorrow. And what register is I?
First value.
Yeah, so that's S1, correct?
Right.
And so what's the second one?
S.
S2. All right, so we have T2 is 1 if we've met your condition. So we can do one of two things here. You can either branch it for the equal case, or we can branch for the less than case. Let's do branch if equal. Let's stay consistent with the TGO. So branch if equal, meaning that I want to do S1, S2, and num instruction. Now, why do I want to do that? Tony.
What?
Yeah, why do I want to do this branch if equal? What else is in this case here?
Less than.
What else besides less than?
Equal to.
Equal. Very good. So I want to branch if they're equal, right? So therefore, branch if equal, num instruction. And I'm going to say +1, and you're going to see why in a second. So last portion, this part right here. This is your last part of your algorithm. So our temp register was T2. So we're going to do BNE, T2, 0. I'm going to stop here. Now, why am I doing branch not equal for T2? What's the value of T2 going to be if we meet the branch condition? Correct. Well, it's going to be 1. So that means if I want to branch, it's not going to be 0, correct? So therefore, I want to branch if they're not equal. And therefore, I'm going to put num instruction here. And the reason I'm doing num instruction +1 is because I want to branch to the same instruction with both of these, because this is all one case. And so there's some number of instructions, and therefore this one will branch to 6. Let's say I have 5 instructions here I want to go past. So this one will go here, and this one will go the same instruction because it's -1. So let's say I have 5 instructions here. We do my work. I have instruction 1, instruction 2, instruction 3, instruction 4, instruction 5. And let's say this is jump return RA, theoretically. What is the value of num instruction? I want to jump to jump register. 5. So I want 1, 2, 3, 4, 5, correct? Why is it 5 and not 6? Program counter item PC plus 1 from the register, right? So this is 5. So if num instruction is 5, what's num instruction plus 1? 6. Very good. Okay. And then I should put 3 here. Do branch equivalent. First val, second val, num str, and then we'll do plus 1, and then we'll do this here. Oh, I see what it is. So put this here. If opposite case contains an equal sign. So there's an algorithm to figure it out. So let's go back to, let's change up the problem here. So I have section 5, right? So we have this, we've done all this, we've come up with an algorithm. That might be a cool algorithm, make a TGO next year, that'll make life easier for everybody. So let's say instead of star first less than or equal to second, let's say I make this greater than, first is greater than second. And let's say, like we have here, first is in, let's say it's in, let's make it in T0, and second is in A2, right? So, first step, what's my opposite condition? Right? Right, so that means, what is my next line of code going to be? Set less than? Yeah, we do temporary register, we'll just say T5 for now. T0, very good. And A2, very good. So next step, does my condition contain an equal sign? Yes, it does, right? First is greater than or equal to second. So you do branch if equal. We do the same order. T0, A2, and then some sort of number, right? And then what's my last step? Branch not equal. And what are the values here? T5 and 0. And this, whatever this value is, this will be, we'll say plus 1. So let's change this to, since it's less than or equal to, let's just change that to less than. Let's do this one more time. So I've changed that from less than or equal to, it's now just first is less than second. So what is my jump condition? I'm sorry, branch condition. I is greater than j, right? I'm sorry, first is greater than or equal to second, right? So what's my first line of code? So here we go. So we had first I is greater than second, right? Yeah, so it's called very good. Right? Why was it the opposite way? It's greater than, right? So we want to flip it. So the good way to do it is less than. So that means second is less than or equal to first, which means this one goes here, and this one goes there. So does my opposite condition contain an equal sign? Yes. So branch of equal. And I do A2, T0, and we'll just call it X plus 1. And so then what's my last? Branch not equal. Call this T4, 0, and X. So there's one last condition here, right? Let's call this greater than or equal to. Very good. So what's my condition? Very good. First less than second. So what's my first line? Set less than. Call it, we'll just say T4, and then we'll say this is T0 and A2, right? Does my opposite condition contain an equal sign? No. So no branch of equal. So what's my last? Branch not equal. And what's my first line of code here? T4. What's the next one? 0. Very good. And just num instructions, right? We don't need to do a plus 1 because there's no equal. Yes, to here.
Why is it T0? Isn't that a temp?
Yeah, it is a temporary register. Previously in the code, I'm going to delete this. And I'm going to show you why that is. So previously in the code, we are passing the value first by as a pointer, right? So we're loading it. We do this loading into. We have to store it. We have A1, right? We store it, and then we load it from so we have jump 12, and we jump down to 12. So the first thing we do is we get this value from A1, which is our value in data memory of first, and then we load it into T0, and that's how we pass by reference. So that's So T0 was first. There. Any other questions about this? Yes.
So the branch address is relative to the current instruction.
Correct.
Position. Is jump addressing the same?
Jump addressing is the actual number in the. This is actually a really good question. Okay, so let's go to, I believe it's section 4. It's section 5. It's on the MIP screen sheet. Makes life easier. Okay, so we have these instructions here: R type, I type, and J type. Correct? So this is the answer to the question. Except one other thing. What other thing am I going to request from you on the problem?
What do they do?
Yeah, I'm going to expect you to have like a sentence description of what they do. Draw, name, and define. That's what the TGO says, right? So make sure if you do all 3 of those, you get all the points. So first thing we do is we look at the actual instruction. So branch is here, branch of equal, branch not equal. So it's the immediate value is going to be PC plus 4 plus branch address. Branch address is what's going to be contained in the immediate value. So therefore, it is relative to PC plus 4. If we look at jump here, the PC is going to produce the actual jump address. And so when we go down to the instruction types, what's going to happen is, if I have a branch, I'm going to compare these 2 results in the ALU, if they meet the branch condition that I want, and then what I'm going to do is I'm going to take this value, and I'm going to do branch addressing. Now, if you recall from one of the sections, it's section 6. Section 6, at the beginning, where we have all these different instruction types. This will be another question, 6.3. You can definitely expect this tomorrow. So immediate is just the operand is a constant within the instruction itself. So that's an I type. You have, A equals B plus 6, right? So 6 is going to be in the immediate value. So register, what this means, you all should understand this now. This is what you're going to follow when you write your coding assignment. So this is kind of a combination of coding and project. So you get the 5-bit value from RS, right? And then I have this 5 to 32-bit decoder here. So you all coded a 5 to 32 decoder, right? So you get a 5-bit input in, you get a 32-bit value out, of which only one of them is going to be your specific register, right? That one that comes on the output, you can hook that to each register's read line. Remember how we have those read and write from SRAM? You can take that out, and as you do your loop, do I read this if I is 0? And one of these values of your output of your decoder is going to be 1, and you're saying, I want to read that one. Just give me that on the output. And you write a function, or you're going to write a function, where you have a 32-bit register, and you're going to get the Q value from each SRAM. And you're going to put that in an array, and that's going to be your output here. Does that make sense? I got a few questions about this. So this is the flow of how that's done. Base addressing is where we do branching. Go away. Branching. So base addressing, what we're doing, I'm sorry, this base addressing is load word and store word. So we get our register value out using the same code, and then we get this immediate value out, right? So that's 16 bits. And then we're going to sign extend 16. So we look at the most significant bit of 16, and we just replicate that 16 times. Because the most significant bit will indicate whether it's a positive or negative number. Now, if we go, so I know I'm jumping around here to answer the question, but this is a good combining concepts type question. So if we go here, remember how yesterday in class I was mentioning there's an add immediate instruction? But if we look down here, there's no subtraction immediate instruction. And the reason why that is because we take advantage of this compiler-driven encoding of the micro engine. We're able to reduce the size of the controller by just saying instead of doing an instead of doing sub-I, we'll just do add-I and do a 2's complement on the number so we have the negative number. So you just take the most significant bit, extend by 16, so that's how you code. If MSB is equal to 1, concatenate those two together. If it's 0, have the 16 zeros and concatenate those together. So then, jumping around to all these different things, this is good. So we concatenate it, and that result is going to be one of your inputs to the ALU. And then the register value, so that's your base address, right? And this is your offset. And they go in and get this produces the exact location in data memory. Now to tie into another concept we talked about from the code here, to kind of go back to your question you asked earlier. So here, I have loaded the value of S1 into data memory in A1, right? Do you recall when we were talking about memory hierarchy, which is another part of the exam, and I said one of the reasons, what's one of the main reasons why we have cache in the first place? Storing, you're on the right path. Storing data for what purpose? Get it fast, right? Storing data to get it fast. So what we want to do is, you see here, every time I access T0, see T0, 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 and T0, right? So here we have 1, 2, 3, 4, 5 accesses in the code. How much, on average, how much time longer does it take to access data memory than it does a local register in this?
5 times.
Times what? That's some factor of the number. 5 times 20. It can take up to 100 times slower, right? So we want to load this from A1, from in the data memory, into T0 to improve performance. So the only times we want to change that is if we actually change the value. So here we added add-I, we increment star first. So I can tell you just from this that we created this pointer for first, and we have T0 and T0, so I can tell you without looking at the rest of the code that I'm incrementing a pointer. Now when we change it, that's when we have to update it. So the next line of code is store word. So that's why I remember in the first section I had you write those big chunks of that paper, and one of them is that we're supposed to have access data memory for load and store only, and everything else is register access. This is a really good example of why we do this and why it's important for you to know. Because when we want to improve performance, because you want to have high performance execution of compile code, we have just taken 495 nanoseconds off the execution of that by doing these load and store word instructions. So does that answer your question in more detail? Okay. So did that answer your branch question? Very good. Right. So that's the next question. Oh, Brian, you have more.
Why did you need the?
Oh, you know what? I just realized I didn't completely answer your question. Sorry. All right. So PC relative. This is branch, and pseudo direct is jump. Right. So this is the end of this. So you actually take the 26 bits from your jump. So it's actually hard coded into the instruction. Then you multiply by 4, shifting left 2 to get 28. And then we take the PC plus 4, which is automatically there, and we concatenate the 4 most significant bits. And this goes back to your program counter, which goes to the instruction memory.
I understand why you're multiplying by 4, but why are you concatenating the 4?
Oh, because the reason why is just like anything else, it's a 32-bit data path, right? So in theory, what you wanted to do, you could just say, if I know that I'm only going to have this many instructions, then it would be only 28. But here's the thing: you want to be able to account for those 4 other instructions. So in theory, you have a large instruction memory that contains 2 to 32 instructions. You could actually account for that by being able to increment. The only way you'd be able to add 4 and change that PC plus 4 is if for some reason it was like one of the last 3 instructions, which in this case it will automatically be accounted for by multiplying by 4 anyway. So that allows, by doing this, we are allowed the full range of 32-bit, 2 to 32 instructions. That's kind of a hack around it. Does that answer your question? Kind of.
I'm also confused. Why would shifting left make you go from 26 to 28?
Because if you're shifting left by 2, what we're meaning is you're going to take the original 26 bits, you're going to concatenate, just probably would be a better way to say concatenate 2. You're just concatenate 2 zeros, but it also is shifting left by 2. But you're not, in most cases, like if you have 32 bits and you're fixed at 32 bits, and you shift left by 2, those 2 most, this is actually a really good question. So those 2 most significant bits get shifted off and they just go away. Right. In this case, they're not. You're going to have 26 bits, and you're going to concatenate 2 zeros, and therefore it's going to become a 28-bit bus. Okay. So that's how you're going to code that. You just say 26 array, and then you have a 28-bit bool array, 0, 0, and then just loop through the next ones, and then you're done. So there's some combining a test question with a coding problem. Does that answer your question? Mm-hmm. Okay. Okay. Anybody have another question? So that was one question answered in 45 minutes. Like I said, I'll stay here as long as you guys have questions.
I have another question.
Sure.
Back to the assembly code.
Okay.
In the beginning, you store S1 to data memory, I guess?
Store, yeah, here, right?
No, above at 3.
Yeah, okay,
and
so here.
Load it a couple lines later. Why not just keep it at S1?
So what am I doing here? What am I doing here? So I'm jumping to 12. Oh, no. Okay, I see. Good question. So here's what's happening. Lines 1 through 5 are preparing us to be able to call a function. So here, I need to have A0, A1, and A2, right? Those are my 3 function argument calls that I can do. So if you're looking back at the MIP screen sheet, I know I keep going back and forth, but it means you're combining concepts and hopefully learning something. So we go back to our register names, right? We can have up to 4 values in a function call for arguments, A0 through A3. So we're going to do A0, A1, and A2. So we're preparing for it. And so going back to the line of code, our function call, we have to do array. So array is a base pointer to S, that's probably S0. So I'm just, going to add, so A0 needs to be equal to S0. So I can do add I, A0, S0, and 0, or I can do add A0, S0, 0, right? Next, we have to get the value of first, which is an S1, into data memory, right? So I have A1. I'm going to create a pointer here, and I need to get it to the data memory. So I have this register value, so it's going to be S1, and I can say where I need this value to point. Now, earlier in the problem, I state the following, and this is important. The initial instruction, you may load any pointer to an integer to any location, right? So what that means is, here I have 7, and this goes these first 7 values. So using byte addressing, we know that 10 is going to be contained in the first 4 blocks, right? So these are going to be all zeros, 5, 6, 7, 8. So hopefully this can conceptualize byte addressing for you. That second one, third one, and then the fourth one, 8, 10. So this most significant bit, middle, and then least significant. So they put those all together, and then this is going to be the 0, 1, 2, and 3. And so going to the second value, 4, 5, 6, and 7, it's 2. So it's going to be all zeros, all zeros, all zeros, and it's going to be 1, 2, 3, 4, 5, 6, 1, 0, right? And so we're going to be using the principal. Remember, one of your questions tomorrow is going to be define the principal locality and differentiate between the 2 types of locality. What are those? Very good. So what type of locality am I taking advantage of here by putting them all together? Spatial, right? So here's what's going to happen. Since I'm using 4 of them, I'm going to have 0 through 3 is the first one, 4 through 7, 8 through 11. And so, Karanthi, I'm picking on you because you did this during my office hours. What's the next one going to be?
11 to 14.
No, it's going to be 12 to 15. Off by 1 error. It's okay. Happens. And then what's the next one going to be? Somebody's been real quiet. Matthew Carpenter.
16 through 19.
Very good. See, somebody else. Tydo. What's the next one going to be? Off by 1 error again. Yeah. 20 through 23. And 24 through 27, right? So this is 1, 2, 3, 4, 5, 6, and 7. 0, 1, 2, 3, 4, 5, and 6, right? So this becomes 0, 1, 2, 3, 4, 5, and 6. So that means, so that means these are what all the array values are going to be. So therefore, we need to pick the next location where we want to load this value of 3. Taking advantage of what type of locality? Spatial. Where is the most logical place to put it in data memory? 28 through 31, right? So, to answer the first part of your question, what I'm doing here, and then to answer your part of your question too. So, this line of code, where I say 32, right? Yep. Yeah. So I should have said 28. Now, 28, what this means is I'm creating this as the base pointer to the pointer in data memory where I'm going to place this. So I say in the problem that you assume all registers are loaded to 0 unless otherwise stated in the code. So A1 is 0. So adding 0 plus 28 becomes 28 in the add I, right? So that means it's now pointing to the 28th byte in data memory. So I need 28, 29, 30, and 31. So here's where A1 is pointing. So the next line of code is going to be store word A10 S1. Because in the load word and stored instruction, the instruction, which is the 16 bits, getting back to one of your questions from earlier, that's going to value is going to be 0. We assign extended to 32. We add A1. So this contains an add, right? And then that's going to point to the location in data memory where I want to store S1. So this is going to be read address, if you recall from the data path, and this will be read data. Because that will allow us to get our location that I want to store it in. I think of it as a locker, right? Let's say you're in middle school, right? And the 7th grade lockers start at locker 32. Start at locker 0. and you are 8th in alphabetical order. So you have 7, starts at 0, goes to 6, goes to 7, you go to 7, then you put your backpack in there. Your backpack is the local register. Right? Think of it, here's a good analogy. Think of class. For local registers and data memory. If you had 3 textbooks, right? And for this course, and I said, all right, first problem is out of this textbook, second problem is out of the next textbook, third problem is out of the next textbook, right? Would it be smarter for Xavier to have all 3 textbooks here, local and registers, or do you think it would be smarter for him to have to go back to his apartment or condo or house, whatever we have, and get the second textbook and come back? Or are you going to get the third textbook and come back? That's what local registers do, and that's what loading and storing does. Now, what a pointer is that it means that if you have one copy, let's say of a USB where you're doing the problems on, right? And you keep it with your, and this is the assignment that you're going to turn in. Let's say you're working on code. And you work on the first problem, you work on the second problem, you work on the third problem here. The copy that's on your USB, if you brought it here and take it back home, is the same copy, and that's like passing by reference. Passing by value is if you have one set of code and you work on it at home, and then you bring a USB and you get a completely different set of code that you change, and then come back, and then your classmate turns in the first set of code, right? So that's the difference between passing by value and passing by reference. So what we're doing here is now we're putting the copy in data memory, and then what we're going to do is we're going to jump down to instruction 12. And then we're going to change everything back in data memory. And that involves that loading and storing that I told you about earlier that improves the performance. Now to get back to here, we jump back. We say it's going to be jump 7, right? So we get back up here, and that's going to do the rest of what's in main. So we did some code execution. And then I'm done. I get to return some. And then I'm here. So now I have this value of first that's in data memory in A1 that I have updated. But here I want to use S1. Right? So what I need to do is I need to do a load word operation after that to be able to get the current copy. So I load word S1 0 A1. So that allows me to get the current copy that was updated in the function, go to A1, load it back into the local registers in S1. And that is why we do store here, to store it there, so that when we call the function later, we can do all the updates. And when we get updates here, and we have changes, we load them back in so we can then finish the function here, and then we jump 0 to conclude the problem. Does that make sense? Good. Is this all starting to come together? I'm hoping that for some of it is. Next question. Let me ask you, what are some of the things that I'm going to see while you guys are crawling through? What are some of the things that you expect on your exam? Other than this, a problem very similar to this.
2-to-1 multiplication.
Okay, yeah. So what's specifically about 2-to-1 multiplexer? Why am I specifically using the multiplexer in the problem? Right. So in section 5. I put it in section 5 for you guys, so that way. All right. So we go back up here, and it's very similar to, this is what I've been alluding to, 5.3. It's the same thing from the green sheet, except with the definitions. And then I added this problem. This is a subset, but then you can do this bigger problem here. So you can ignore all the literal gate cost stuff. But this is the type of problem. So we look at what I'm stating here, right? Given the following functions, I will give you a function that will contain some combination of A, B, and C. Right? Will not be more than 3 variables. Design the circuit using a 2-to-1 multiplexer and any other necessary gates. Use a Carnot map to derive the input functions for each of the 2 inputs to the multiplexer for each variable. You may only use AND, NAND, OR, NOR, and inverted gates as the input to the MUX for the final solution. So what is the concept that I'm testing here? Shannon expansion, right? Very good. What is Shannon expansion? One of you actually wrote the word-for-word definition on the quiz. What's the whole point behind Shannon expansion?
Reducing gate costs.
Correct. How so? By using a and 2-to-1 mux. You're on the right path here. I like it. So use the 2-to-1 mux, and you're right. You're reducing gate costs. So the whole point is, I want you to notice something interesting on this solution here. Notice how normally if you're doing a K-map, what you'd be doing is you want them all overlap. So you would do this, you would do that, right? Or this, or something like that to make it as, efficient as possible. So here, you're not doing that. And the reason why you're not doing that, and the reason why you're able to get away with this in order to reduce gate cost, is to use a 2-to-1 multiplexer. So we can use that 2-to-1 multiplexer to eliminate race conditions. So therefore, when you're doing the K-maps here, you only want to do it on one line. And the variable, now stating it in the problem, use a Carnot map to derive the input functions for each of the 2 inputs. So if you look at this Carnot map, there's 2 inputs to the multiplexer for each variable. So in this case, it's A. So the first thing you want to do is you want to get your function and draw out a truth table. So if you draw it's A, B, C, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? And then function is your output. So you look through here, A naught, C naught is one case, so that means it's 1. None of these are met. 0, 1, 0, so that met. A naught, C naught does meet it. And then 0, 1, 1, BC does not one of these conditions, so it's 0. 1, 0, 0 does not meet it. 1, 0, 1, AC is one of those. 1, 1, 0 is AB, so it's met. And 1, 1, 1, it meets all the conditions, right? So what we're trying to do is go about A and try to relate the function output to A. Now, Shannon expansion means that I can have any function where if it's 0, the output is some sort of function. So in this case, if A is 0, then this is an output. If A is 1, that means this is an output. Now we can look at this really clearly and see that this is C naught and this is B or C, right? Sorry, B or C. Does that make sense? So using the K-maps, you can justify that in this way. So the way we did this here is you draw the K-maps for A. You use 0, 1. Remember, you use gray encoding along axis when you have 2. So it's 0, 0, 0, 1, 1, 1, and 1, 0. So you go to your truth table and write this out. And then you see here that the cases that it's 1, it's C naught, right? And then 1, it's B or C. If we do it for B, so that means your 2 inputs are AC and this is B. Therefore, you go here and you see that 1 and 1, these happen to be true along when the input to the multiplexer is 0, when A equals C, right? So A equals C is also A XOR C. So you're allowed to do an XOR as one of your function types, right? And then here, it's 0, 0, 1, 1, and 1, 0, right? So it's not A naught or C, so it becomes A or C naught. And then the third case is about C. So this becomes not A B naught, or it becomes A naught or B, which makes that A naught or B for this one. And then here it's just A. So what I'm going to do on the exam, in the interest of saving time, is I'm going to tell you the exam, the practice problem. It's more complicated, the exam problem. What I'll do is I will say where the two variables are where the two functions are A or B about C, about variable C. That means I want this one. If it says AC about B, I want this one. If it says BC about the variable A, I want this one. So the about variable, whatever, means that I want that variable to be the input to the multiplexer. And the other two variables will be along the opposite axis. Does that make sense? So we'll be posting this again as a video later, but that will be your how you do this problem. So let's do this problem again. So I say, given the following function, word. So say given the following function, f equals AC or A naught, B naught, design the circuit using a 2-to-1 multiplexer. So I'm just going to go ... and any other necessary functions. Derive for each where the cooperate. There we go. Use a Carnot map to derive the input functions input functions for B and C about the variable A, and then you may use whichever one. So what's the first step we want to do here? Do the truth table. So let's start. Let's move their epic pen here for a second. It's a little too epic. So we can insert a table. So we have A, B, C, and function, and that gives us, we'll do one last line. So we have A, B, C, and F. So if it's 0 and 0 and 0, what's my F going to be? 0. Oh, is it? A naught, B naught. Means if it's 0, A is 0 and B is 0, that means F is going to be 1. Good try though. So 0, 0, and 1. What's the function going to be? 1. Not going to be F. It's going to be 1. So 0, 1, 0. What's this going to be? 0. Very good. If it's 0, 1, and 1, what's it going to be on my output? 0. If it's 1 and 0, 0, what's it going to be? 0. 1, 0, 1. It's going to be 1 because of A and C. 1, 1, and 0, what's it going to be? And then 1, 1, and 1. It's going to be 1. Very good. So next step. We have to design a Carnot map. Oh, I'm sorry. Does anybody have a question? Okay. Next, we want to design a Carnot map, right? So we're going to insert table 2. So that means, what are our two variables going to be for the horizontal axis? B and C. And then what's the other variable going to be? A. So this becomes 0 and 1. And this becomes 0, 0, 0, 1, 1, 1, and 1, 0, right? So for 0, 0, 0, what's our value here? 1. 0, 0, 1. 1. 0, 1, 1. And 0, 1, 0. 0. Okay, 1, 0, 0. 1, 0, 1. 1, 1, 1. And then 1, 1, 0 is, okay. Next step. What is when A equals 0, what's the function going to be here? What? B bar, very good. So f is equal to b bar. And then when a is equal to 1, therefore, what's the f going to be equal to? C, right? So then the last step is to draw out the function. So we have b and c as our inputs. So what do I want to do here? Okay, good. I want to have a mux. And then what's my other input to the mux? A, very good. And so what do I want to do here? Invert B, and where does it go? And then what I do for C? 1. Boom. That is that. Yes, come on. Because, okay, so going back to when we had, we're going to erase that for a second. Put this down here. So when input to 0, this means when A is 0, we have to look at, we do our Carnot map, right? So we look at what these have in common. 0, 0, and 0, 1. So this was B, and this is C, right? So what do these values have in common? B is 0, right? So when B is 0, that means the output's going to be 1. So that means B inverted. That means when B is 0, what's going to happen is it's going to be inverted. It's going to go to 1, and then A is going to select 0 here. So that means 1 is on the output. I'm sorry, before I get to you, did I answer your question, John Walter? Okay, yes.
So in a sense, will we have one more like this where the grouping of the midterms is more obvious as to what we should do? Like on the last one, there's different ways to group them.
I actually just made this question up off the top of my head.
Well, right, but if we're on the exam there.
If you're on the exam, I mean, okay, so let's go through this problem again to answer your question. Well, I think what you're saying is it's more complex. So if we did A, B, right? So we go through here and we find where A and B are 1 and it changes. So that's the only change we're going to make, right? But it's going to have a change on our output. So we have to go back through here. We go to 1, 1 when it was C, when A was 1 and B was 1 and C is 0. That's going to change our output. So now the question becomes, what is this function here? What's the result going to be? When A is 1, B or C, correct. B or C. So to answer your question, this simply becomes, when you have B, you're going to invert it when it goes to 0, just like normal. And then for C, you're going to have your input here to an OR gate. So 1, and that's your output. Now to answer your overall question, the purpose of the multiplexer is to reduce the complexity of the input. So if you're doing like 5 or 6 AND gates, you're off. It shouldn't be much more complicated than this. And then now you've gone through an exam for me. If I see that you're really close, I'll try to poke you in the right direction. So if I come by and I see like you're like, oh, you did this by mistake, oh, you're so close. Look at your K-map, right? If I do that, don't erase your whole thing. Look for one minor thing. So does that make sense? So that's the whole problem. Okay, so we've covered Shannon expansion. We've covered seed coding to MIPS. Does anybody have any other questions? Actually, I'm sure you guys have tons of questions. I won't try to guide the instruction. I'll let you guys get it. Yeah, Roderick, then McKenna.
All right, could you do like a memory access time?
Okay, what specifically? Okay, back to specific.
Just like know like a problem.
Specific question. What specifically do you not understand about it? When I think about what I'm making you think about what you do know. I'm making you think about what you don't know.
Could you go to like the problem
Oh, okay. So the answer is I don't know anything. Okay. I really don't know anything. All right. So recall at the end of section 6, cache, memory. Remember, we're going to have a problem that looks similar to 6.4, right? Remember that too? Average memory access time. But you see, once you practice these, they don't take very long. We did that whole problem like 3 or 4 minutes. And that was me getting interrupted. But then we have this last question where we talk about this big one here. So this was 6.8. Given a cache hierarchy with 8 words and a cache access time of 5 nanoseconds, here's what you will have. You have something like this. And then you have to write out this. And then you have to write out, so this is your direct associative. And this is your set associative, right? So the problem is going to be written as follows. Given a cache hierarchy with 8 words and a cache access time of 5 nanoseconds, I'll probably change the numbers to make sure they're nice and neat, so you get a neat little answer on your exam. And memory access time of 20 nanoseconds, I could make that 100 nanoseconds. And the following set of memory accesses, and I'll give you a set of decimal numbers. A, if the cache is a direct map cache, show the sequences for accessing the cache and calculate the total time. So that's part A. So the first thing you're going to do before you do anything else is you're going to take these numbers and convert them to binary. And so you need to know how to define the index. You need to know how to define the tag. You need to define how the data, and you need to know how to define the valid bit. So now that I've jogged your memory, Roderick, what's your question? Do you have a specific question? No? Do anyone want to help him out with a specific question about this? Because once you work through a couple of these, it comes kind of intuitive.
About when you change an N to Y.
Okay. So what does V stand for? Valid bit. So if I have so going back to the definitions of cache hit and cache miss, if I try to put something in tag 010, is this a cache hit or a cache miss? Automatically a miss. Why is that? Nothing there. So there's 2 steps to accessing a cache element. One, you check the valid bit to see if there's something there at all. And if it is there, then you can use your transition look-aside buffer virtual memory question on the exam. Then you go to the next stage. If it's not there, you just go. So this is going to save you some time. So valid bit Y means it's actually there. So what I would do if I were doing this problem is I have my order here. And so I've converted all these here. So let me move this over so I can draw this out and show you this all. So we have, let me make this red so it's easier to see. So you have, I call it index, V, T is for tag, and then M is for memory, right? So how big is my index going to be? Now I'm not saying, now let me rephrase this. Tell me why it's 3. Log of 8. And what is 8? No. 8 is not 3. 8 is 8. What specifically is 8 in the problem?
Number of blocks.
Yeah, with 8, cache hierarchy with 8 words, right? So log 2 of 8. So for direct map, our index is going to be 8. So let me do this again. I is going to be 0, 0, 0. Actually, let's build one up here. Insert table. So now it's going to be 8. So you know that I need another one here. So index, valid, tag, memory, right? Showing you guys how to use Word while you're at it, right? So index, tag, valid, tag, and memory. All right, so index, since we know it's 8, we go 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? And so all the valid bits are going to initialize these zeros. So leave them alone, fill this out last. And so our order, let me get you our order. So my order was 22, 28, 31, 22, 16, 13, 31, 8, 5, 13, 8, 5, right? So first thing we're going to do is we're going to convert them all to binary. So 22 is just 16 is 8. So that's going to be 4, 6, 0, 0, 1, 1, 0, right? 22, 28 is going to be 16 plus 8 is 24. 8 is 28, so that's 0, 0, right? And then 31 is going to be all ones. And then 22 is already there. 16. Most of them will be. And then 13. Actually, I can just save us a little space here. $13 is going to be 8. 4 is 12. That right. So that's 13. And then 8 is going to be 0, 1, 0, 0, 0. And then 5 is going to be 0, 0, 1, 0, 1, right? I miss any? 22, 16, 31, 28, right? So first one is going to be 22, right? 16 plus 20 is 22. So we look at the index, which is this, 110, right? So 110, that automatically makes our valid bit yes. And we go with the tag, which is 10, and that goes mem 22, right? That's our first step.
Are we making that table in the test?
Yes. Yes, yes, you will. And I won't, the list number list will not be as long as this. Just so you know. Okay, so next is 28. So we look at 110, 110, and then we have 11, memory 28, right? So we now know, so we can keep track of 22 miss, 28 is a miss, right? So what's our next one? 31, what are we going to do? 111, we go here, we go yes, and then this is what? 11, memory 31, 31 miss. Why am I keeping track of these hits and misses up top? We have to do, we're going to have to do performance at the end, right? So this allows you to figure out how easy it is to do. So next, 22 is a what? Hit. 22 hit. So what's 16? Miss. 0, 0, 0, 0. Tag is 10. M16. And 16 is a miss, right? So nuts 13. Yes. And then 10. So 0, 0, 1. M13. So this becomes 13 is a miss. And then what do we add again? 31 is a hit. And then what's next? Let me at this point I can now drag this out over here. Okay, so what's next? 8. So what is 8? 0, 0, 0. So what do we have to do? We have to change this to 0, 0. Then 8. So 8 is a miss, right? Yeah, you're right. 0, 1. Okay, so what's next? 5. We already have that there. So we just changed that to 0, 0. And this goes from 13 to 5. 5 is a miss. So what's next? 13. It's also a miss, so we go back to adding 8. So what's next? 8 is a hit. And then 5, miss. Right? And so this becomes 5. And so let's say, if I say the problem where a hit is 5 nanoseconds and a miss is 100 nanoseconds, what does this make our overall performance? T equals what? Okay, 5 times, and then how many hits do we have? 3 plus, how many misses do we have? 9, right? So therefore, so it equals 15, so 9, 15, right? Oh, very good point. So if I state the question as we access the cache, right? And then you go to data access, right? Or the same thing as data memory equation. Well, we're doing memory hierarchy and you're doing cache hierarchy and this problem in the same exam. All right, I'm going to take this out of this problem, the performance, because they were on different exams when I've given this in the past. And if I want to combine concepts, but I'm already asking you about this on this exam, so I'm going to take that part out. No need to test you on the same thing twice. What was what here, man? Somebody went, man, I want to be tested on the same thing twice. I'm a glutton. So, okay, so the second part is I want to do it as a set associative cache. So that's the second part. So I'm going to get rid of this whole performance part, but I'm going to say, and I'm going to get rid of calculate the total time, show the sequence for accessing the cache. So if I want to go back here, what am I going to make here? Right? So somebody explain it to me. What's my size of my index going to be? No, that was in 2. Why? Other than I'm just throwing numbers up. Throw your hands in the air, I just don't care. So set associative cache, right? So it's a two-way set associative cache. So if I'm thinking about backing logarithms, what's log 2 of 2? 1, right? So basically that means you're just dividing it in half. So if you're doing a two-way set associative cache, you're having 2. So I'm dividing 8 in half. What's it going to be now? 4, right? So we have our row, and then we have 1, 2, 3, 4. So we have invalid, index, memory, valid, index, and memory, right? So this will be index, valid, tag, memory, valid, tag, and memory. So we're doing the same order here, right? 22, 28, 31, 22, 26. So what's the first thing I'm going to do here? And so one last thing, you want to 0, 0, 0, 1, 1, 0, and 1, 1. And then, oh no, you keep that, then the tags are different. All right, so same order, 22, the same order. This will be more complicated than will be on your exam.
Why did the index change? Like, why did the size of the index change?
Okay, so that's what I was just explaining. Okay, so here's the thing. So actually, this is a problem that's going to be a really good example. What we're doing is called as two-way set associative.
Right.
So what we're doing is creating it in sets,
Right.
and the whole goal is to improve performance. So here we just have a cache where we have 8 blocks.
Right.
What we're going to do here is we are going to have two sets of 4 blocks. So that's why the index changed to 2. Okay. Does everybody understand what I just said? I'm happy to say it as many times as it takes before everybody in here gets it. Set associative, it's in sets. So 2-way means 2 sets. So 3-way, it's not possible because it's not divisible by 2. So it would be 4-way. So if I did a 4-way, what would my index be? 0 and 1, right? And then I would have 4 sets of 2. So here it's 2 sets of 4. And typically you don't want to go above 4-way. If you do performance equations, and you can do that in grad school, you'll see that it typically tails off after 2-way. So we have 22. What do I want to do here? Going back up here. Let me copy and paste this again, even though you don't need to. So that's our order, and there's all your binary. So first one is going to be 22. So tell me which one we want to do. 1, 0. And then I want to do what I want to put here. 1, 0, 1. Valid is yes, and this is going to be memory element of 22, right? So now you understand the difference here. You know, if you're talking about using load word and store word to do the pointer, tag and index corresponds to a pointer to the block, and then you're going to have some actual value. So this demonstrates that you understand the difference between value and address. So next one is what? 28, which is 0, 0. You go yes, and then this becomes 1, 1, 1. Memory of 28, right? So what's next? Yep, 1, 1. So what's next? 0, 0. And here's where it comes into play. To get back to your question, Xavier. So now we would normally have to perform a swap. So what this allows us to do is this says yes. This is still initially a miss. So everything's a miss up to this point. So everything up to 31, 22, and 16, they're all still misses. And why? And getting back, Ryan Mays, because you asked about this. Why is that still a miss? Exactly, that is empty, right? So that's why getting back to empty, getting back to the valid bit, why that becomes important. So go tag is which one are we doing? 16. So it's 1, 0, 0, and memory of 16, right? So what's 13? 0, 1. So this becomes yes, and this becomes 0, 1, 1, memory of 13, and then 13 is a miss. So what's next going to be? 31 is a hit, right? So here's an interesting thing. 1, here 13, and 1 are this one. Sorry, which one was it? 22, 1, 1. Oh, okay, never mind. So it'd have to be the same. So we haven't hit that yet. So 31 is a hit. So what's next? 8. What is the tag? So what's the index? 0, 0. So we have 2 in there. Which one do we replace? Least, yeah, very good. Least recently used. So we're going to replace 28 with we're going to replace 28 and we're going to replace it with 8, right? So this becomes 0, 1, 0. And that becomes memory of, instead of 28, becomes memory of 8. Okay. So then 8, we go 5. What's 5? 0, 1. So we just load it into here. And then we see 13, 8, and 5 are all there, right? 13, 8, and 5. So now we go 13 hit, 8 hit, and then 5 is a hit. So how many hits do we have here? We got 1, 2, 3, 4, 5 this time. Previous time we had 3 hits, correct? So now by using this, the exact same values, you're going to have an improvement in performance. So on your exam, so you understand the purpose of the problem and what you should be looking for when you're doing this. When you do direct and set, here's how you know you've done a right answer. Set associative should have improved performance, so there should be more hits, right? Additionally, I'm going to want to test you on your knowledge of least recently used. So there will be one instance where you will have to choose one of those, right? So if you go, oh, I had to do one least recently used, this one had 3 hits, this one had 5 hits, I'm pretty close. But you'll get the overwhelming majority of the credit if that's how you work it out.
On the test,
Hmm?
we can just draw like one chart and just go back and erase.
I would, yes. That'll save you a ton of time too. That's the preferred method. So yeah, you can do that. As long as you have this information on your exam, relative to, of course, to the, don't do this. So I'll get the occasional student who will just try to memorize this answer, and then I'll have, you laugh, but you know, desperate times call for desperate measures, and you hope, right? So it's going to be off enough to hammer you on points. So as long as you demonstrate relative to the numbers I give you.
So when you overwrite, you're missing as well.
A miss is either it was empty, the cache miss is either it's empty, or if I were to say, okay, so I have 16, right? So 16 is my least recently used. So let's say I said 16, I had 4, so let's say I have 20 is my next number here. If I added 20 to this list, what I would do is I'd say, well, I have 20 is going to be 16, 20, 16 plus 4 is 20, right? So I would go, index is 0, 0, since those are the 2 least significant bits. And I say, is it an 8? No. Is it 16? No. If it's in neither of those, it's another miss. So what's going to happen is, I say, which one of these two did I least recently use? So I go back and I see 8 was closer than 16. So I replace 16 with 20, and it goes 1, 0, 1. If I did that in the previous problem, right? If I added 20 here, right? So I would go to, so which index would I want to use here?
0, 0.
1, 0, 0, which goes to 28. And overwrites that one. So in that case, both of those were missing. But you see here, you have 5 elements saved in the cache, whereas in here, you have 1, 2, 3, 4, 5, 6. So we're already using more effective use of our space. And that is taking advantage of spatial locality.
What was the other type of locality?
Someone help him out. What's the other type of locality? Temporal. And so what's the difference between temporal and spatial locality? And what's temporal?
Reference. If it's reference already, then it's reference to data.
Exactly right. If you reference one specific piece of data, you're going to more than likely use it again. If in spatial is if you reference a specific piece of data, you're more than likely to use the data elements that are close to it. So going back to the concept of data memory, we have this data memory element. So we have our base pointer, right? And we have everything together in the array. If you're more than likely to access something in an array, you're going to do loops, you're going to modify it, you're going to do something else. You're more than likely going to use these. So knowing the principle of locality, temporal and spatial locality becomes very important in understanding how to improve the performance of an advanced digital system. Okay, next question. Sorry, where are we at? All right, so we're already at an hour and a half. Good.
What is the major difference between virtual memory and physical memory?
Okay, very good question. So let's bring this up. This is section 6. You are specifically referencing. I'm going down here and talking about memory, and we're talking about this problem 6.9, right? where I give you some sort of page size and physical address, right? So this problem will answer your question. Given a 32-bit MIPS data path, so it can hold up to 2 to the 32 potential number of addresses, right? Where the page size is set at 4 kilobytes. So 4 kilobytes, what is that power of 10? Here's the easiest way to do it. What's 1 kilobyte to the power? 1 kilobyte log 2 of 1 kilobyte is equal to what? 10. Very good, right? So that's because that's 1024. So if it's 496 or 4 kilobytes, it's just 10 times 4. So what does this become in log? 12, right? That's because that's just 10 plus 2. So here, this means I have 4. That's how many pages I have, right? Page size is set at 4 kilobytes. And the number of physical pages allowed in memory is 2 to the 18. Show how virtual mapping is performed and how big is the physical memory. So first thing we do, log 496 is 12. 10 times 4 becomes 10 plus 2 in log. So the first 12 bits of your what I mean by first is LSB, your least significant bits 11 to 0 are the page offset. So this page size corresponds to 4 kilobytes, right? So that's the size of the 4 kilobytes. So remember, byte addressing, we shift left by 2 because we have 4 bytes correspond to 1 word. So one page is going to have 2 to the 12 of those together. So that's a page offset as opposed to byte offset. Does that make sense? So you see this, first thing you're going to see in the problem, page size, 4 kilobytes, 2 kilobytes, 1 kilobyte, 2 to the 10, 2 to the 11, 2 to the 12. The least significant bits are in the virtual memory. So the rest of the virtual page number is going to correspond to just the rest of the address. Now what that means is, if we go back to this previous diagram here, we are issuing a virtual address, and this is going to be 32 bits, right? And then we have a memory management unit, and this is what the problem is testing, understanding of memory management unit. And then we're going to tell you some sort of physical address where it is actually in the cache. Now we may not necessarily have 2 to the 32 bits of memory in cache. And that's where the second part of the problem comes into play. So the second part of the problem is the number of physical pages is 2 to the 18. So I have 32 minus 2 is 20. So that's how many bits I have here to represent the number of virtual pages I have. So I can actually do this by going to the physical memory and having more than that represented in the actual non-volatile RAID arrays. So what's the difference? I have 2 to the 18. So that means that my physical address can have up to 18 bytes, sorry, 18 bits here. So here, what this drawing does, and this is all you really have to do on the exam, you might not even have to do that, well, except for full credit. Just say, write this, log 2, 492, write 2 to 32, say, you can say virtual, draw this and just write 20 and 12, and you go translation here, and then 18 physical page, and 12. So you see how this goes up to 12 to 29, so that means it's 18 bits as opposed to 20 bits. So if this problem, and here's a more accurate version of the problem. So let's go back to our Word document. So we're given you will definitely get a wrong Word document. So let's say we have MIPS data path is 32 bits, and we have a page size of 1 kilobyte, and the number of pages in physical memory is 16, right? There we go. Then I say show the size of the virtual, show how virtual mapping is performed. So I'll scroll down here. So what is the actual page offset here based on this problem? 10, right? So log of 1024 is equal to 10. Therefore, that's the page offset. Or you can even write this. Let's see if we can come up with this simple solution as possible. Page offset is equal to log 1024 is equal to 10, right? So let's see, number of virtual pages is equal to 32 bits minus 10 is equal to 22. And then number of physical pages is equal to what? How many? 16. So then you can draw this. So then you go virtual as you can get. Let's see. So first you draw the page offset, and you're going to write 0 to 9, right? And this goes 10 to 31. And then you have translation. And then the last thing you draw here, page offset is 9 to 0, right? And then how many bits are here? 16, right? So if we start at 10, where's this going to end at? 25. There you go, full credit answer. Just show me that you understand page offsets. Show me understand that this means that the difference is virtual pages, and that it translates to a physical page. So get to the other thing that I want you to draw on the exam. I want you to draw this guy, right? So this combines what's happening in that page translation, right? So I don't need it to be this big. Just show me that if you could draw 3 or 4 in the transition look-aside buffer, 3 or 4 in the page table, 3 and 4 in the physical memory, and disk storage, right? You draw this out, you'll be fine. So here's what this means. We have a valid dirty reference bit, and they don't always correlate in order. Otherwise, the easiest way to do the translation would just be to have a mapping where the 16 next least significant bits that were in the physical page is correlate identically to the virtual page. And the reason we can't do that is because we're trying to extend past the number of physical pages by using disks. So that difference, if we had up to 2 to 32 in disks, we could actually use that by swapping out pages. So the first thing we do is we try to improve performance by using our transition look-aside buffer. Transition look-aside buffer, we check to see if it's there. If it's there, we just go into physical memory and get it. If it's not there, the next step we do is do the page table, which the page table consists of your direct memory access or your direct set associative. We're dealing with cache. And then page table, because remember, virtual memory is trying to use the physical memory as a cache. So you check here, is it there? Yes. Here, so basically, show me, your two cases are, it's here, or it's not there, right? So if they're both being pointed to here, you can do 3 cases. So you have 1, 0, 1. 1, 0, 0, meaning it's being pointed to, but it's not being pointed to in there. So here's the simplest way to do this, right? You have virtual memory, so you have your page, right? Virtual page. You have transition look-aside buffer. You draw your valid bit, your dirty bit, and your reference bit, and memory, right? So you go here, go here, go here, right? And then you go down to your page, and then you do the cases where it's 0, 0, 0. You just go directly to disks. And if it's 1, 0, 1, it goes there. And if it's 1, 0, 0, it also goes here. But the difference is here 1, 0, 1, they're both pointing to value in transition look-aside buffer. That corresponds to this case here, where we have a value look in the TLB. That means it's been recently used. And it's also going to be in the page table, 101. So if you draw that out, demonstrate knowledge, you'll get full credit. Does that answer your question? Good. Any other questions? See, I talked about memory hierarchy. We have memory hierarchy where we had direct and set associative. You need to tell me the principal locality and the two types. You need to draw me the 3 types of MIPS registers, MIPS instructions. You need to draw me the 5 types of memory addressing. And then you need to draw me how the transition 6.28, how the transition look-aside buffer goes in there. And then the other problems are going to be you have to do a you have to do the physical page conversion. You have to do a direct and set associative problem, and then see the next problem. Trying to think if there's anything else. Let me double check and make sure, because I think we've hit everything in terms of what will be covered. Yes. Okay, so you want to go over. We're gonna have time to do that on the exam. Well, great. I'll just do a creativity challenge. Do not this next week, but the week after, where you can write restoring and non-restoring in C. How does that sound? There's no way I can ask restoring and non-restoring question and that massive C problem on an exam. So since we'll do that, we're also not going to do 6.30. Well, no, this problem on here, I'll leave that there. That's pretty easy to draw. So typically, when you guys have the memory, you've memorized everything. Typically, the problems where everybody has it memorized takes about 25 minutes. And then I have 20 minutes saved for your C problems. That's 45 minutes. They have another 30 minutes to do your set associative and your virtual memory problem. Oh, and your Shannon expansion problem, which I'm reducing by only having you do 1 case instead of doing all 3 cases. Well, now here, I'll phrase it this way. That'll be nothing outside of that scope will be on your exam. I may take this out. I may not, depending. I'm going to try to get an honest feel for what I think you can accomplish. Let's see. I asked you about TLB. I asked about NMU. I asked about disks. No, we're not doing this problem. Because, not just because I'm trying to figure out time, but also because I'm asking you about disks. This has to do with pages, TLB, and then by doing this problem, you are doing memory management unit. So I've already asked you everything, so there's no point in asking that. Okay. No. Asked a lot about that on coding. So we have so nobody asked me about the average memory access time, but I think that's pretty straightforward, 3-level. How do you write out that equation? Does anybody have any other questions relating to C code? C to MIPS? Yeah. Why not? While we're here. Well, you got me around.
I really just don't understand like the format of when you add, like when you putting stuff in certain places. Like I really just don't understand the format of it, like the syntax of it.
Okay. So let me see if I can copy and paste this. Okay, so actually, you know what? I probably can do one better. Section 5 lecture notes in Word. Picked up where you left off, right here. All right, so we have this code. So let me copy this. Let me copy the solution. Let's just go into here, right? And then let's bring up the MIP screen sheet. All right, so they are in opposite orders. So we're going to do add first, because the first thing I want to do, since in array is first, all I want to do is move the value of the base pointer of array into a argument variable, right? Argument register. So we're going to add here. So let's compare the difference between when I add and MIP screen sheet. In fact, I can move this even closer. So first thing you're going to want to do when you start this, code should start on line 1. Because when you return 0, you want to jump to 0, which is going to be outside the scope of what we're asking on this exam. So the first thing I want to do is going to do add. And so I want to put it into A0, right? Because that's my first argument. And so the value is contained in S0. And then in this case, I can do 0 here. And in comment, I'm going to put your other acceptable right answer, add I, A0, S0, and 0. Now, let's compare and contrast. So here, in assembly language, RS and RT are added and put into RD. So in this, RS, RT, and RD. Where the confusion typically happens is because when we go to our instruction formats, they're in the opposite order. RS, RT, and RD. Now, this was done because at the time, assembly code, especially in BCPL, B programming language, is just like this. It's in this order. I want to take these two values because you could have more than 2. You can add 2, 3, 4, 5, and then have them in here. But when we go, if you recall in section 1, I talked about how the design of the code was based off of improving performance, and then everything else in terms of ease of coding was compromised. So this is what they were talking about. When we go to section 7, and we go to the layout of the data path, here, right? So if I'm able to zoom in, the reason why they do it this way is because if we had to do it in a different order, we'd have to put a 25 to 21 would have to contain RD, but that's if it was an R-type instruction. If it's an I-type instruction, it would have to be RT. So we'd have to have some sort of decision here going into a write register, and then we do read reg 1, and then read reg 2, and they would both come out here. But what they decided to do was this layout was simpler and less confusing. So they decided to have the design opcode 31 to 26, RS, RT, RD. And they could easily make this decision in the write register. And then this 32-bit bus that comes back from mem to reg doesn't interfere with most of the control signals. It does kind of interfere with ALU op, but by and large it doesn't. Whereas if it was up here, it would interfere with 8 of the 9, so that causes more area. Okay, does that answer your question? Okay, good. So for the MIP screen sheet, which you'll have on the exam, you can understand that RS and RT, and then you can actually see equals RD, and it's in the order in Verilog. And I can show everybody else what I was just showing Xavier. If you see it in Verilog, what this means is that the assembly code that you're going to be writing on the exam is going to be in the exact order, add. So if I'm doing A0 here, S0, and register 0. It's in that order. You will have that available to you on your exam. Does that answer your question? Good. Okay. Next question. I see some people are starting to fade a little bit since we've only been reviewing for 2 hours. Any other questions?
We don't have to draw the data path, do we?
No. That would be exam 3. The reason why I introduced it, though, before exam 2 came up, is because a lot of the concept errors that come up, such as what Xavier was just asking about what the order of the instructions are, the difference between that and how it is in the instruction format, is typically solved when I can show the data path and say, here's why. So I wanted to try to eliminate as many conceptual errors before the exam came up. Any other questions? Wendy's texting her friend for a question. McKinnon's listening for questions from Regis Philbin. Why is there so many data path questions? Why can't it just be a magic unicorn? Okay. Does anybody have any other questions? All right, well, in that case, I'm going to stop recording here, and I'm going to upload this, and I am going to go walk my dog.